This is a video about the hydrogen atom emission line spectrum. So we've talked about this a little bit in class, but I don't think I gave you the terminology. But when an electron is as close as possible to the nucleus, we would consider that to be ground state. For hydrogen, there's only the one electron. For other atoms, there may be electrons kind of filling these levels, and then maybe the ground state would be out here. As long as all of the other places are full, it's still as low as possible in energy as possible would be considered ground state. Excited state is when the electron, let's say this is where it could be, but now it's moved out further, higher in energy, away from the nucleus. That is considered excited state. So we've seen this in the lab. We saw this in the flame tests. The heat caused the electrons to absorb energy, and they absorbed the energy in packets of energy called photons. So with photon is a particle of electromagnetic radiation. And it carries a specific chunk or piece of energy. So the electron absorbed that energy, it then moves out further from the nucleus and becomes excited. Then it will come back, and when it comes back, it will give us different color waves depending on the jump. So if it's a small jump back, then you might see a red color. If it were, we had many levels and maybe the electron was here coming back down, then maybe you would see a blue or a violet color with higher frequency. So how do we get those atoms to gain the energy in the first place? We've talked about the flame tests. I actually put them in the fire. Causes the electrons to absorb those photons of energy and then to return back to ground state and release that color, the energy of the photon, but as a color wave. But we can also do this through electrical current, and this is what we see in the different neon lights. This is also what occurs in some of the fluorescent lights. It's a little bit more complicated because there's a coating and things within the light too. But for the most part, when you, an old-fashioned light bulb, which not many people have anymore, but the kind, other than the retro ones, but the ones with the little filament, that filament actually burns out when the light bulb is done. This is an incandescent light bulb. That works in a different way. That one, it actually just glows that color, but the other ones that have like a gas in them, their electricity is causing the electrons to move out, become excited, come back down, and when they come down, that color is what we see. So the hydrogen in the emission tube is kind of a pink color. If you were in school that day, you got to see that. I'm going to show it through the video too, and we'll see what kind of colors you see. And then when we use a spectroscope, which is kind of like a prism, it sends the light in and it bends it and allows us to see the parts of the light that you wouldn't otherwise be able to see. Then we get to see these. This is called a bright line spectrum. This is not hydrogens, but it's, I don't know what element, and it is specific to the element, so it's like a fingerprint. And classical, thinking about light as a wave would have made us believe that everything would have been, every possible frequency would have been available, and that we would always see continuous spectrum. We do see the continuous spectrum when we look at true white light, sunlight, but otherwise, when you're looking at an element, you only get to see certain parts of that spectrum. And that is going to lead us to, the quantum theory or the quantum model of the atom, which is that there's only certain energy amounts which correspond to certain frequencies that can be seen because the electron is only able to change. So for the red color here, from the Pogel, if you remember, that was, if we were to give like rings here, 2, 3, it was going from 3 to 2. So it was a lower energy transition, and we got that specific red frequency. When you were in the higher frequencies, that was n equals, so we have 4, 5, and 6. That was 6 down to 2, gave you that really high frequency violet color. So only certain colors are allowed because only certain energy transitions are allowed for the electron. And this is not an equation that you need to know, but this is a way to kind of think about it. So the energy that's either absorbed or released by the electron is some whole number multiple of this equation. So it's quantized, which we're going to talk a lot more about, but it's kind of a weird thing. So if you think about, like, quantized would be like you can only absorb, you could have 1 skittle, you could have 4 skittles. Like the skittle would represent this energy of the photon, and you can only have 1 or 2 or 3 or 4. You cannot have 1.3 repeating skittles. So skittles are quantized, if that makes sense. If not, we will talk much more.